In the previous sections, we discussed some of the gravitational forces that shape the entire universe, including the fundamental forces that govern the behavior of matter and energy. However, even though we have begun to understand the forces that influence the tangible things around us, there is still one mystery lurking in the background that has yet to be solved. That is space. Think about it carefully. What exactly is space? If you ask a physicist or a philosopher what space is, you will surely be overwhelmed by a bunch of words that sound profound yet meaningless. Is space an endless void that serves as the backdrop for all things in the world? Is it something that fills the gaps between objects? Or is space a type of substance related to fluidity, like a bathtub filled with water? What is space? It doesn't seem like a very difficult question to answer, but if you challenge your intuition and re-examine the question, you will find that it's hard to come up with a clear answer. Most people imagine space as an empty field, like an empty warehouse. Based on this view, space is literally an empty void that just sits there, waiting for something to fill it. It's like when you go to park and need to find a parking spot. The word spot in this sentence refers to the space people intuitively think of. Starting from this concept, you might think that space, even if not filled, is an independent existence. If the combination of all matter in the universe is finite, you could always walk far enough to leave everything in the universe behind. At that point, what would lie before you is absolute void and endless world. In other words, space is an infinitely expandable void. This description of space sounds reasonable and aligns with our daily experiences. However, we must remember the lessons from earlier. Whenever we assume that something is definitely correct, we should take a skeptical attitude, step back, and double-check. More importantly, we should consider those theories that can explain the same phenomenon with completely different mechanisms. Maybe we missed something, or there might be some related theories that, under their framework, our examination of the universe is just a special case. Now, since we are re-examining space, why not look at those theories about space that seem reasonable? Could we assume that space must coexist with matter? What if space itself is just a relationship between matters? If this were true, then pure space couldn't exist because the concept of space without matter doesn't make sense. To use an analogy, if you want to measure the distance between two particles, you first need to have two particles. Without any material particles at the end, the concept of distance no longer exists. So, what is a place without matter? It's certainly not empty space. This perspective is quite strange. It goes against our intuition, especially when we have no concept of non-space. But just because a theory is odd doesn't mean it lacks physical significance. Which explanation of space is correct? Is space an enormous void waiting to be filled, or is it something that must coexist with matter? In fact, we can be sure that neither is true. Space is definitely not a huge void. And it doesn't just exist as the relationship between matters. The reason for saying this is because we have observed phenomena that don't support any one theory. You see, when you propose a theory based on the phenomena currently observed, and the theory perfectly explains these phenomena, then the theory is usable. Until one day someone discovers a phenomenon that cannot be explained by the current theory, then no matter how perfect or intuitive the theory may seem, you have to abandon it. So why do we say that neither of these two theories is correct? What phenomena have people observed? They found that space can warp, ripple, and expand. What does this mean? If space itself is just a concept, then it shouldn't produce deformations like bending or expansion, just as it couldn't be torn apart. If space is used to define the size of objects, how can we measure the bending and expansion of space itself? For most people, the concept of space curvature is difficult to understand because we've always mentally visualized space as an invisible wooden board. You might imagine space as the stage of a theater, with its floor and walls made of hardwood planks. There is no force in the world that could bend such a stage because it's an abstract framework, and it isn't part of the universe itself, only the parts within it are. Unfortunately, things are not as people imagine them to be. To understand space using the advanced concepts of general relativity, you must treat space as something with physical properties, rather than viewing it as an abstract theater stage. You have to make an effort to imagine the properties and behaviors of space. The matter in the universe affects space. You can squeeze space, bend it, or even deform it. So, space is a physical entity that can ripple and curve. This means space isn't a super large empty room, but more like a large, sticky mass. Normally, objects can move freely through this sticky substance, just as we can walk around a room full of air without noticing the surrounding air molecules. But in certain special cases, this sticky substance will twist, and the trajectory of objects moving through it will change accordingly. In addition to twisting, it can also shrink and ripple, causing the objects within it to deform. Comparing space to a sticky substance isn't perfectly accurate, but it helps us understand the concept. We must understand that the space we are in right now is not necessarily a fixed, abstract thing. On the contrary, it is a real, tangible thing. Perhaps a ripple of space has just passed through you, or maybe we are being stretched along some strange direction, but we are completely unaware of it. In fact, it wasn't until recently that scientists discovered that this sticky substance is always moving around, rather than staying quietly in place. What strange things can this sticky space do? It can do a lot of weird things. First, it can expand, meaning that even if the objects in space don't move, they will get farther apart from each other. Imagine sitting inside a large mass of sticky substance, and suddenly this sticky substance wrapping around you begins to expand. The person sitting opposite you is also moving farther away, even though the sticky substance between you has not moved. How do we know that space is expanding? Won't the ruler we use to measure also expand along with space? Indeed, the space between the atoms that make up the ruler also expands, and these atoms move farther apart from each other. Suppose our ruler is made of very soft sugar, then it will expand. But if we have a very hard ruler, with a strong bonding force between its internal atoms, this ruler can maintain its original length. With such a ruler, we can observe whether space is expanding. The reason space can expand is because we have already observed this phenomenon. The dark energy we mentioned earlier was discovered this way. We know that the universe expanded at an astonishing speed in its early stages, and this expansion is still continuing today. In addition to expansion, space can also bend, and this sticky space, like cotton candy, can be compressed and deformed. In Einstein's general theory of relativity, this property of space is the essence of gravity. The curvature of space creates gravity. If an object has mass, the space around it will warp and deform. Once space deforms, the objects within it no longer follow the intended path. In a piece of bent sticky material, a moving baseball no longer moves in a straight line. Its direction of motion will bend towards the warped direction of the sticky substance. If space is severely distorted by a very massive object, the trajectory of the baseball could even become circular, just like the moon's orbit around the Earth. Interestingly, we can observe this situation with the naked eye, such as when light is deflected as it passes near massive celestial bodies like the Sun or dark matter clusters. If gravity were an interaction force between massive objects, and not a manifestation of space bending, it should not affect photons, because photons have no mass, their mass is zero. Therefore, only the space curvature theory can explain how the trajectory of photons bends. In addition to expanding and bending, space can also ripple. If you can understand the stretching and bending of space, then the property of rippling won't seem so outrageous. Stretching and bending can propagate through the sticky physical properties of space, and this mode of propagation is called gravitational waves. If space is instantaneously distorted, this deformation will propagate outward like sound waves or ripples in water. This can only happen if space has some physical properties. If space were an abstract concept or some kind of void, such phenomena would not occur. We know that the fluctuation of space is real for two reasons. The first is that general relativity predicted its existence. The second is that we have already detected it. Somewhere in the universe, two massive black holes, unable to escape each other, spiral around each other at a crazy speed, causing huge deformations in the surrounding space, spreading out like ripples in water. Using highly sensitive instruments, we on Earth have detected these ripples in space. You can think of this ripple as a wave produced by space repeatedly stretching and contracting. In fact, when this ripple passes through a certain area, the space at that location will contract in one direction and expand in another. Space is a real entity, not just pure void. This concept sounds crazy, but it comes from our actual experience. Observational results clearly show that the distance between objects in space is not measured against some invisible abstract background, but depends on the properties of this sticky substance in space. If you imagine space as an object with specific properties and behaviors, perhaps we can truly understand its bending and stretching, but this will raise more questions. For example, you might think that what we previously called space should actually be called a physical sticky substance or even physical glue. However, this sticky substance must be contained by another object, so the container holding this sticky substance would become space itself. But based on our current observations and understanding, this container is not necessary. When we talk about bending, the deformation is not the sticky substance distorting relative to some background, but rather a deformation that fundamentally changes the correlation between different regions of space. Of course, the fact that space doesn't need this container doesn't mean that such a container doesn't exist. Perhaps outside the space we are discussing, there is an even larger superspace, which is the true infinite void. Does this situation exist? We don't know yet. If we press further, is there a region in the universe where space doesn't exist? Since space is like a sticky substance, could there be places where space isn't sticky? Could there be regions where there's absolutely nothing? These questions are still beyond our understanding. All physical laws assume the existence of space. When space doesn't exist, these physical laws lose their meaning. In fact, our new understanding of space is something that has only emerged recently, and our grasp of space is still in its early stages. In many ways, we are still trapped by our own intuition. When primitive humans were busy hunting and gathering, these intuitions were quite useful, but the nature of space is so different from what we imagine. In trying to understand it, we must free ourselves from the constraints of our intuition. We can further think, is space flat or curved? If it's curved, in what direction is space curved? Once you accept the idea that space is malleable, some ancient questions are not so difficult to answer. If objects with mass distort the space around them, could space, as a whole, have a region? In other words, the sticky substance of space is not flat. If you poke it, space will distort and deform. But what kind of deformation will it undergo? Will it sink as a whole, or will it stand upright? The answers to these questions could greatly affect our view of the universe. For example, in a flat space, if you walk in one direction continuously, you could walk forever and never reach the end. But in a curved space, things get interesting. If the curvature of space is positive, then if you walk in one direction, you'll eventually return to the starting point from the opposite direction, much like how walking in one direction on Earth eventually brings you back to your starting point. The concept of space curvature is difficult to understand because our brains are not good at imagining such things. Why does space have curvature? The three-dimensional space we encounter daily seems quite stable. What does space curvature really mean? Let's take some time and pretend that we live in a two-dimensional world. Our world would be like a thin sheet of paper. In other words, we can only move in the forward, backward, or left-right directions. Let's assume that this sheet of paper is perfectly flat. It would be called flat space. If this sheet of paper bends for some reason, then the space becomes curved. There are two ways to bend this sheet of paper. One is to make all the curves on the paper bend in the same direction, which is what we refer to as positive curvature. The other is to make perpendicular curves on the paper bend in different directions. You can imagine all the x-axis curves bending downward, while all the y-axis curves bend upward. Eventually, the shape you get looks like a potato chip or a saddle. Now comes the mind-bending part. If all points in space are flat, that means the sheet of paper can expand into the surrounding curves. But if all points in space have positive curvature, it will only have one shape, a sphere. More precisely, it would be a spherical body. This makes our space a closed system, like the surface of a potato. Although the curvature in different places might not be the same, no matter which direction you walk in, you will eventually return to your starting point. This space must be closed. So what kind of space do we live in? Is it flat or curved? In the next video, we will delve deeper into the concept of flatness, explore the possible sizes and shapes of space, and even venture into the quantum nature of space itself. This is Cosmos Unlocked. Stay tuned as we continue to unlock the mysteries of the cosmos.